Hi there, I know we should be talking about the keyboard part of the project, but first let's take a look at the Deep Note and the process it took me to research for it and learn about digital music. Let's do it. So before taking a look at the keyboard part and microcontrollers, let's take a look at the Deep Note and how the Deep Note took me here to make this project, to build a synthesizer. The first idea that came to my mind for the project was build a synthesizer based on the Deep Note. So you only generate Deep Notes. Actually, it will scale up and down as you press the keyboard, just like the project I show you by Bob Miller. But what is the Deep Note? What is the Deep Note? And it's actually a very curious story, so let's just take a quick look. In 1982, James Moore wanted to create a sound that would show everybody what its company was capable of. So he worked for Lucasfilms, a subdivision of it called THX. You might know today, but at that time it was just a subdivision of Lucasfilms. So he created a sound that would show what they were capable of. And he created 20,000 lines of C, and that got translated to 250,000 lines of score. It ran on the audio signal processor. It was a mainframe of the company that just worked with sounds. In the later years, THX would spin off and become its own thing, but that is the story about how the Deep Note was created, But how actually does it sound, Well, if you watch some movies or video games that use THX technology or are THX certified, you probably know it. So right now I'm gonna read with you my work on the Deep Note, and just a quick note here. I'm not fluent in English, but I try to work with English to just hone my skills. So I'm going to show you my work. I made this short PDF about the Deep Note as a work for my graduation. And you can download my work in the link down below. It has a basics to the project, of course, an outdated version of my synthesizer, so take it with a grain of salt. Let's go to the second part of the work, which is about the Deep Note itself. And basically, as you can see, this is a drawing by James Moore. The Deep Note is just a bunch of notes that oscillate between 200 and 400 Hz, and then after some time they go to mezzo forte in intensity, they just go silent, and then they all proceed to their target note, as you can see there. They just span for this short range of sound to 11 notes, each note with more than one voice, and they all go from silent to fortissimo. And after some time, they die out. That's what basically seeing this in this musician's weird, sacred, forgotten language. I learned to read this by just using this table here. A friend of mine, Cassio, just helped me with the music part, and then I proceed to the engineering part. In my short essay, you can see all the notes that he used and the analysis of the Deep Note. And then I made some spectral analysis about the Deep Note, and you can see it's basically very rich harmonically, and then after some time it spans all the notes, and you can see in the top range of frequencies that's some artifact there. We're gonna study that. That's all about Nyquist-Shannon sampling rate theorem. We're gonna see that in the later part of this project, so before we gotta build the engine and then build all the hardware necessary, and then after the engine is done, we can do some filtering to prevent that from happening. Although I'm gonna tell you, my hearing is not that good. After 15,000 Hz, I don't hear anything actually. So the second graph has the frequencies in log, so you can see the bass part in more detail. Deep Note is built with some sawtooth waves, so it's very rich harmonically, and this is basically how you build from scratch a sawtooth only with sines. So you can see it's very rich, goes indefinitely. And then I explain a little bit about DACs and ADCs. So if you don't know what a ADC or a DAC is, an ADC is an analog to digital converter. It basically gets a value between 0 voltage and your max voltage for your circuits and for your microcontroller, and then it converts proportionally to a number from 0 to something. This maximum value is the maximum number you can get with the number of bits you used in the conversion. So if you get 8 bits ADC, you go from 0 to 255, and you can use this method to read analog values from all different kinds of sensors. To use an output, you need a DAC, digital to analog converter, and that uses some different methods but with the same kind of data. You get a number from 0 to something, this something your maximum number with the bits you used. So you go from 12 bits DAC, you go from 0 to 4095 actually, and that will express itself as a voltage. But of course, as you're using a digital number, your analog values will go from step to step. They will not go continuously, and the transition between values will not be seamless, you know? They'll have bumps because you need more bits to get more resolution, and you can create information out of thin air, you know? Your output will have little steps. Then in my little essay I explain a little bit about the interruptions and the use you have. In the software part I explain everything you need to know about interruptions, and that's basically all the knowledge you need to understand all the parts of this project. You need to know a little bit of electronics, a little bit of programming, and a little bit of music. Although I started this project with zero knowledge about music, and I got to learn stuff on the way, and now I don't get that lost. Although sometimes when I'm learning about, you know, scales and chords, it can get a little bit complicated, but we're here to build an engineering apparatus, so that part is covered. For the next videos on, we'll get a little bit more technical. Actually, you go full technical, you're gonna read about the electronics involved, hardware part, then microcontrollers and programming, and after that all the software involved to get, you know, a microcontroller, a simple machine, then make music that sounds nice in the ear. So all you need to do is, if you're not comfortable with, you know, electronics or programming, I suggest you take a basics class. You have YouTube, everything is available these days. I'm gonna be using some really basic concepts of embedded systems, so nothing too complicated. So in electronics we're using a keyboard, buttons and sliders, so basically potentiometers and buttons and diodes, nothing too fancy. I might use 1 or 2 op amps, but you know, as comparators, amplifiers, simple usage. Then from the microcontroller, basically programming, interruption cycles, and of course after this beginning part I started using my oscilloscope for debugging and measuring stuff. So if you don't have an oscilloscope, I try to teach alternative ways of doing what I'm doing. The programming part will be very basically needs read a keyboard, operate this DAC that will generate our sounds and then amplify it. That's it, you know, reading inputs and then generating some waves from some tables, and that's it. Speaking of tables, we have some other acronyms that you need to know. For example, the synthesizer is digital, it's a DDS. It's basically direct digital synthesis. So we get a number and then translate to a DAC. So you can go from DDS on Wikipedia and it will show this fairly complicated diagram, but nothing to worry. Just so you have an oscillator, basically an interruption. We're gonna do this in software, right? And a frequency control register basically counts how many times the oscillator ticks, and then when it reaches the right count, it just bumps the NCO. What is an NCO? Numerically controlled oscillator. This will basically be our LUT, another acronym, lookup table. Well, this table basically is a matrix, so a sequence of vectors that saves the analog values that we want to put in an output as a saved sampled sound, or values from an input from a sensor. And then you can run along this table in a certain frequency and then get that and apply to a DAC. And that just makes a sound. Simple as that. The reconstruction low pass filter is just to get this jigsaw signal and trying to smooth it out, but you can forget about that. So this all basically is a for loop that has a delay, or better yet, an interruption function that is called many times per second. The frequency is determined by us, and I'll explain how all that works later on. And then this function reads the value from our vector, puts in the output, and adds 1. So next time it's called, you read the next vector on that matrix. And that's how you read all the values in this table and in the end you have a sine, a triangle, or a sampled wave. Using a lute sometimes is also called wavetable synthesis, which is sometimes called sampling. It depends. I don't know what is the soft difference between, but I'm planning about using additive synthesis, so you're gonna add simple waves as sinusoids and sawtooth and squares. I'm planning using FM, so applying some frequency modulation, so this frequency we update our lookup table can vary over time, and I'm thinking about using sampling, which is record a complex sound and then playing forth and backward and in loop. And that's basically it. So before ending the video, I wanted to show you some tools I use to actually work on the concepts I'm showing you. So the first one is Desmos. It's a site I use to use some basic calculations, some iterations, some scripts. I use it as a calculator, and I actually use it to plot some stuff and sometimes to use some interactive calculus to just define some parameters in the code. If you guys found Desmos interesting, I can make a tutorial of the basics about it. I think it's a really powerful tool, and being free is just, mind-blowing. So here I just created a simple signal, simulating a sound signal, and I have just the parameters just to make it look messy and look weird. You can ignore all this, ignore this. This is the important part. This is a table formed with n, the number of samples, and for each sample the value of the function. So every time we sample the signal, that's the real analog value, and then when we quantize it, so we make it discrete, we make it digital value, look what's happened. I used round to make a round number, so in that position, in the position we created a sample, we cannot have numbers between the discrete values, right? That's how ADC and DAC works. And this is the difference you get when you're sampling with a lower resolution. Right now I'm having 1 and 2 and 3 as our possible numbers. We could increase this. I will show you later what happens when you increase and decrease that, but this is just a basic example. Then I made a simple function that make it look like it will look in an oscilloscope. So you have the basic steps here, and that will form our digital signal. You can even hide the original function and the analog values, and this will be the output of this function. And as we are quantizing the signal, there will be an error. So I made another function. I'll just put the points back, and then the function of error is this one. And as you can see, there's an error because our resolution is low. So this is a basic graph to show you what happened, and I can of course change the frequency, and you can see our resolution is not that great for a signal that goes up to 32, and you have 32 possible positions. So this is a really low resolution. For ADC or DAC, it would be 5 bits, really bad. You can see the error sometimes gets close to 1 unit. Or 32, that's really bad. So this is another script I made, and this is a little bit more complex, so I'll not explain how it works. I just wanted to look at the graph and just kind of try to understand the concept. So this is a signal that we are sampling, really stupid, really basic, just to show basic concepts. And ignore this middle function here. SR is my sample rate, so now, right now it's 8. But we can increase it, and look what happens. M is the order of magnitude, and the small m is the number. So we can go really high in here, and as you can see, the signal gets closer, but still is bad. Why? Because our bit depth, so the amount of bits we have to sample this, is low. So I'm going to decrease sampling rate. Now I'm going to increase bit depth. See what happens? The numbers get exactly where they are when they are sampled. So our samples now are really close to the real value. What happens when we increase bit depth and sample rate? Well, you got a perfect signal. So that's basically it when we're talking about sampling, be it in output or input. So just to repeat the concept, if that was a little bit too much, sample rate is the rate which we sample our data, out or in, doesn't matter. And bit depth is the amount of bits we have to sample that, so the resolution. And right now I can increase or decrease bit depth in this script, and you can see more bits better because it gets more accurate. And the sample rate, you make more samples over time. And down below here you have the quantization error, so it's a function of both sample rate and bit depth. The bigger both, the better, to a point in which you're not gaining anything back because of the flaws of our design, increasing cost and complexity. So there's a point, there's a sweet spot where you want your DAC or ADC to operate. So remember when I talked about harmonically rich or poor and harmonics and spectrum? So this is the part when it all comes to place. The deep note was built with a sawtooth wave, right? What is that supposed to mean in like when you talk about frequency? Well, a sawtooth is made of many sines, and then you add them up, and then you have a sawtooth. Every signal that is periodic can be built summing sines or cosines, doesn't matter. So that's basically Fourier's work. Fourier had the transform in series, now you're looking at the series, but the transform just work the same. You look at the components of a signal, and here we have all the same signals, right? Well, these are actually different waves, but I'm just summing the first, as you can see here, the first harmonic. So the first harmonic, of course, is called the fundamental frequency. So it's the first harmonic is the fundamental frequency. The other harmonics are multiples of the fundamental frequency. And as we increase the harmonics sum to the signal, look what happens. That's what happens. You get closer and closer to the signal you originally wanted in your system. So there's a pure sine here just for comparison, and I marked 2 points for the period of pi. The first thing to notice is the triangle wave is almost a sine. I can reduce the number of harmonics like to really low. And like with the third harmonic, you already have a wave that looks really close to the ending result. But sawtooth and square are really rich, harmonically speaking. So they need all the harmonics in there to like look really sharp because they have sharp edges. So they need high frequency waves to actually look like the original one. And what we're doing here is getting the complex signal with all the harmonics and filtering all the harmonics up from a place. So right now, third harmonic. So this is like a 1000 hertz signal, right? We have a filter here that after 3000 hertz, 3 kilohertz, but before 4 kilohertz, it cuts entirely the signal. And that's what happens. You get a deformed, weird wave because you just filtered a part of it. This digital signal processing part is complicated. I am studying right now. It's a lot to take in, but just, familiarize a little bit with harmonics and filters, because after the software part, we're going to get there in digital processing, and it's a lot of to take in, and it can confuse you. Of course, you can just look the code, copy the code, and work your synthesizer, but if you want to understand what's going on, I made some scripts here to make things look a little bit, clearer. I made this script kind of like a closer look into a sawtooth, because as I told you, the deep note will be the benchmark for a system. I want to test the system with the deep note. And a problem that we get, and I will show you this in the future, is when you try to make high frequencies digitally and they get closer and closer to a sample rate, the definition here, the resolution limits you, and you need to introduce a little bit of jittering. We will see this after the engine of the synthesizer is built, so you can just take a chill pill here and relax and enjoy the trip, But there's another thing that goes on when you're trying to sample and just input and output. It's Nyquist-Shannon theorem about sampling, and if your sampling rate is lower than twice the frequency of the original signal, you're gonna get some artifacts, and in music and sounds you're gonna get sound artifacts, and that's really bad. So here I made a little script that sum the harmonics of a sine. You can lower this, and this is a sine wave basically. Here you have the signal you want to achieve with the microcontroller, the original one. In red, the one we are building with the samples. Here is the derivative, you know, so the angle of that function, the original one, and here the derivative of our red signal, the one we are building from samples. And here the error. So you can see the more you add harmonics, the more you add a derivative, sharp edges. So when you're gonna build our sawtooth wave and you're gonna use the deep note, there will be the need for a filter, because these harmonics here that will come to here, you have really high frequency harmonics because the sawtooth wave is really harmonically rich. They will cause some artifacts, and I make this script to show you that when you filter a sawtooth, it starts to go back to look like a sine. I think this is interesting at least. So the last tool I use a lot is a combination of this online tone generator by Zenowski. I don't know how to read that. And this is basically an online tone generator. It generates any sound you want, but with multiple options. So you can use sines or squares or triangles or sawtooth, and then you can listen to it just to have an idea of what you want to generate with your synthesizer. When it comes to another important function is to actually use a spectrum analyzer to actually analyze it visually, something that you're hearing, and then compare it to another sound. But where can you get a signal analyzer, a spectrum analyzer? Well, there's a free one, and I'll show you. So the name of the program is Friture. That sounds like fried stuff in Brazilian, so I don't know what it's called like that. You can look at the spectrogram here. So in this part is a spectrogram, here is like spectrum analysis, and this is a basic oscilloscope, right? So the spectrum show all the frequencies, spectrogram shows a history of it, so it's showing not only what I'm saying but over time. And here we have a scope. Look at the shape of our voice or signal. And the interesting thing is, you see vowels are super rich harmonically speaking. Look at how many harmonics we have. I'm gonna make a single note and try to keep it. I'm not a singer, and look how crazy the spectrogram go. And you can see this is the fundamental one and all the harmonics, basically infinite. And you can do that to the signals we generate with the synth and some sines and cosines to form a new wave. That's how additive synthesis work, with some signals to form a new one. So I'm gonna play a sine right now at 440 Hz and see what happens with the microphone. There is a little bit of noise here, but otherwise a pure function, right? Look at the spectrum here. 439. You got a perfect signal and noise. We have a background noise here. It's really rich. I have the computer, I have my fridge. Very noisy place actually. So when I'm playing a 440 sine and change to a triangle, what happens? Let's test it. So the sine is not that pure. That's probably because of all the stages in generating sound in the computer. There's some distortion, a little bit of distortion there. It just happens. Look how rich we get when it switches to triangle. You want to see something crazy? Let's go to square and sawtooth. That is just a sea of harmonics. So that was the square wave. Now let's go from square to a sawtooth and look at the harmonics. You can see it has even more harmonics and stronger harmonics. That's basically why people use sawtooth waves in synthesizers. They are really easy to make, DDS or analog, and they are very rich. So if you want to use subtractive synthesis, you make a really rich sound and then use a filter to take something back. And the triangle is really rich. So that was basically the second video of this video series about building a microcontroller based synth. That was all the basic knowledge you needed to get up to date where I am right now. If this video was a little bit confusing to you, I suggest you look up some concepts and get familiarized with them, because we're gonna use them basically over and over in the next videos about hardware and mainly about constructing our signal based on sampling and a DDS and etc. I hope this video wasn't too confusing. I hope you liked the video. Post questions down below, please do. And I'll see you on the next video now about the keyboard, refurbishing, cleaning it, making it work, and then reading it with a microcontroller. Bye bye.